This is ELEC120, problem sheet 1, question 2, solution to part E. So this question is worth 6 marks. So this is quite a large number of marks for an exam question, and it's a drawing question, and these are traditionally done pretty badly by students. The maths questions are fine, the drawing questions seem to be more difficult. So you're told, given positive charges Q1 and Q2, which were described above, are of equal magnitude, sketch the electric field structure and equipotential lines for this system. So the main thing here is they are both positive, and let's just look at it. So it's not particularly difficult to do. I don't understand why these are done so badly. So they're both positive. So what I've done is this is Q1 and this is Q2. And the difficult bit of this question is the interaction between the two charges. So because these are positive, they're going to repel. However, the easiest way to do this, if you've got two charges in a line, is consider that anything sort of to the left of Q1 and to the right of Q2 are going to behave as if there were no other charge there. So this is a positive charge, and it's got electric field lines radiating out as you would normally, and the same for Q2 over here. Where they interact, there's some region where initially the electric field is out as it would normally be, and then it starts to be influenced by the other positive charge and it veers upwards. I did a little demo of this in the lecture so you could have a look and see what happened to the field lines. It's a bit difficult to draw, but just do your best, and anything that looks vaguely sensible is fine. And just the same, so this is reflected symmetrical down here, and the same for Q2. So the electric field is normal, radiating outwards, and then it gets influenced by the other charge and radiates upwards. So that's the electric field lines. The equipotentials are always perpendicular to the electric field. So close to the charge, there it's a normal circle, and you can see there. And that's what we've done for both ones. And then when you get out to here, you need to have these again perpendicular to the field lines. This isn't a perfect drawing, but it's not bad. And that's what happens. So essentially, we've got this kind of gap in the middle, but that's what happens with two positive charges. So if you can draw that, that is 6 marks for you. I'm also going to answer part F now, because it's a very short question and it kind of follows on quite nicely from drawing off electric field lines. Part F asks us to state what is meant by a conservative field, and this again is worth 4 marks, so these are just really important concepts that you need to get your head around. So a conservative field basically means that if work done in the system is independent of the route taken and no energy is lost in a closed loop, then the electric field is conservative. So that's basically saying there's no friction and there's no other losses in the system. So that means that the work done will be returned if you go back to the same starting point. So where do we do this in the lecture notes? We did this here. So assuming it's a conservative system, if you go from A to B, doesn't matter what route you take, the same amount of energy will be used. We can also extend this to our other example, which was this one. So I'll go down to the answer. So this is assuming if you go from point A, doesn't matter which direction you go, if you go all the way around, if you come back to point A, if the field is conservative, no work will be expended because the start point is the same potential as the end point. And that's the answer to that question.